Okay, so as promised, I want to prove that the two different ways of defining a length for curves in Euclidean space actually coincide for C1 curves. Recall that this length here is defined as the supremum over all n and all partitions of such summations. So n is the number of divisions, and the partition is the partition of the compact interval we're talking about. So you do gamma of ti plus 1, gamma ti, and you take the norm. So this is the difference of one blue node from the next blue node in my picture, and I goes from 0 to n minus 1. This is the right indexing here. And if you do all possible divisions of the interval and then take supremum, that's by definition your length of gamma. Now the goal is to prove that you will get the same value if you took derivative of your curve and then you took its norm. That means you computed the speed of the curve and then integrated that. So I want to prove this now. Let me first make a few quite easy observations that nevertheless will be kind of pivotal to our proof. Number one is that if you add nodes, you only increase that summation. So adding more nodes, that means increase n and put new intervals, will help that sum. So because well, if I add a new node, what it means is that instead of that blue that connects these two, first you connect these two and then these two, and then the summation of this and this will be bigger than the previous summation by triangle inequality. So that's it. And the other observation is that the length of gamma is never less than the distance of the endpoints of the curve. Well, because you can take n equal 1 and then you have to, there's only one partition, you have to take t0 equal a and t1 equal to b. So that is also quite understandable. If you travel somewhere else and then come back to b, the length you traveled will be more than the going along the straight line. And the observation 3 that I want is what is called the mean value inequality. So for such C1 curves, and actually for any nodes, but here I want to state it for the endpoint. So if you have a C1 curve, then gamma b minus gamma a. So the usual R1 one-dimensional mean value theorem is that this is equal to gamma prime at some intermediate point times b minus a. However, such a theorem is not in fact true for vector valued functions. The only thing we have is an inequality. So the claim is that if you have a C1 curve defined on AB, then there exists some C such that this inequality will be true. So you will see how I will use all these observations in the proof. So the number one thing that I want to prove is one of the inequalities. So first I'm going to show that this length is always less than this integral. So as usual in most analysis proofs of equalities, you do inequalities and then you get the equalities. So because everything is defined through infimums and supremums and Riemann sums, so that's just the way it is. So how do you approach such a problem? Well, given any epsilon positive, there exists some delta positive such that, so what I'm gonna write is just saying that any Riemann sum that you write will be already close to your integral, provided that these intervals you take are short enough. Okay, so the mathematical way of writing that down is that such that for any partition of this interval AB, if this the biggest distance you have for delta ti's, and I'm gonna say t's i's, so the way indexing here I've done is you go from 0 to n minus 1. If the biggest of these intervals is less than delta, then I can also make it an equality, it doesn't matter. Then this Riemann sum, so the way I integrate gamma prime, is, of course, I do partition. I write a Riemann sum by choosing Ci. So here, for any choice of Ci in the interval ti plus 1, this summation delta ti, this Riemann sum, strictly less than n, is already pretty close to the integral. So gamma prime tau norm d gamma. Okay, so this thing, unfortunately, I ran out of space here, will be less than epsilon. Okay, so that is saying that any Riemann sum I write, any choice of these intermediate points C that I have, will get me to epsilon closeness of the integral. Okay, so now for any partition used in definition of length gamma. So remember, this length gamma is defined by partitioning and then doing a certain summation. We add nodes if necessary, so that the maximum delta ti over I becomes less than or equal delta, because that's the right delta from above. As observed above, this only helps, this never takes it down, only increases the sum used in this definition of length gamma. So if I prove that the new partition that I have after adding these nodes is also less than a quantity, the original one will also be less than that. So what happens after these modifications is that when I write summation I equals 0 to n minus 1, then what I have is the distance of ti plus 1 from ti. Of course, they're images. What I then write for this is, first I apply the mean value inequality. So I replace the interior by I know that there is some Ci, and I compute the derivative there. I hope I have the derivative up there in writing the mean value theorem. Yes, so this is here, because I'm gonna send you the PDFs of these as usual in the description. And then this will be distance of Ti plus 1 and Ti, that is just my delta Ti. Now here is where I did all that Riemann something, because this now tells me that this summation, no matter where Ci's happen, is epsilon close to the integral of the speed. So this will be tau, d tau, the worst will be epsilon away. So I get this inequality. Now notice that this quantity here that I have is independent of any partition. All of a sudden that partition is out of the picture. So, and this is now any partition I have. So any partition you give me, I increase it by adding nodes, and the increased quantity is already less than that quantity. So I don't want to repeat what I said, and I'm gonna just write that length gamma, which is supremum of all such summations. So if every element is less than something, then the supremum is also less than that. The price is that the strict inequality has to, of course, be turned into a possible equality as well. So you get this, but epsilon is arbitrary, and that means we can take actually epsilon to be equals 0 and still have the same inequality. So gamma prime tau nor d tau. So this is the inequality that I was going to prove for step 1. Now, in an interesting way, I'm going to use this inequality to prove the equality of these quantities. That's why I kind of thought this proof deserved to have its own separate video. So part 2 is as follows. So define S of t to be the length of the curve, not gamma, not the original curve gamma, but its restriction to the interval a to t. Okay, so when I restrict the function gamma to a subset of its domain, I still have a function on a compact interval, and then I can talk about the length of gamma as well. Now, what I know about this function, some immediate observations, is that S of A is 0, for instance, and S of B is just length of the original gamma that I had. But we want to prove way more about this S function as follows. So let's see. So S of t plus h, and that means I'm going to compute its derivative, minus S of th. Okay, so this thing by definition and a little bit of easy observations is equal actually to the length of gamma from t to t plus h. So I'm going to do positive h. The negative one is just symmetric. What do I know about this quantity then? Well, from one of the observations in the beginning, the length of a curve is never less than the distance of its endpoints. So this will be distance of, what are the endpoints? Gamma t plus h minus gamma t and norm. And now from the part 1, that's where part 1 appears to help with part 2. This is less than the integral from t to t plus h of the speed. So gamma prime tau d tau. Okay, and now let me divide by h, or maybe not, divide by h, and let then h descend down to 0 in limit to get So here's something interesting. When I divide by h, h is just a scalar. It can go inside this here. So you can put this h here. And now the limit of this, what is the limit of this fraction if h goes to 0? That's by the very definition of derivative. This is gamma prime computed at time t, but everything now has a norm outside this. So it's norm of the limit, and it goes through. So this one then equals s prime of t. Well, this is also proving at the same time that s prime of t does exist. So this, if I show that this fraction of s converges, then it also means it's differentiable. So I already take a shortcut and write the notation s prime of t. But I'm not cheating because I am at the same time proving that it is well defined. And now I have 1 over h here. This quantity here is just average value of this function over the interval t to t plus h. Because it's a continuous function, the average value of that when h goes to 0 does also converge to the value of that function that is being integrated at the at time t, because these intervals crush down to t. So you have the equality. S prime of t equals that function. Now, by fundamental theorem of calculus, this means that s computed at any time t equals integral of that function, because this is its derivative at time tau d tau, and this is from a to time t. And also notice that at a you have 0 equals 0, so you don't need any correcting constant anywhere. And so we proved actually more, but all we were interested was in the particular value of t equal b. So s of b, which is just length of gamma, I made that observation above, is equal to, from a to b, gamma prime tau d tau. An amazing proof with lots of amazing tricks, so you may have to watch this video again, or I really recommend that you download the PDF as you watch these videos. So beautiful. For a C1 curve, we prove that this definition, which is quite very different, actually does equal this one. Thanks a lot. See a video that was previous to this video discussing the fundamental and philosophical difference between these two quantities, although they are equal, and one of them generalizes to the metric space curves. Guess which one? Please do comment if you have worries or corrections about the proofs. I will always welcome them in the comments. Have a great one, and see you in more videos.